Hello, my name is Joaquim Barros and I'm the scientific mentor of CVTest. Today I will present the software FEMIX, that is a software based on the finite element method for thermomechanical engineering problems, specialized on the simulation of the nonlinear behavior of concrete structures. FEMIX includes a large library of types of finite elements, a set of point, line, and surface nonlinear springs to model the diverse contact conditions with the supports, includes several interface finite elements to model the inter-element contact, also embedded line finite element to simulate the reinforcement bars, and also special embedded finite elements for simulating fibers in the context of fiber-reinforced concretes. It is possible to perform static and dynamic analysis with material and geometric linear and nonlinear behavior. And in sim analysis, it's possible to have several nonlinear models simultaneously. And it is also possible to simulate time-dependent phenomena like concrete maturation, creep, and shrinkage. It includes Newton-Raphson method, arc length techniques, and path-dependent and independent algorithms. And for solving the system of equilibrium equation, it is possible to use direct and pre-conjugate gradient methods. And in the last years, we couple FEMIX with GiDs for the pre and post processing by defining the FEMIX problem type. So in this slide, we see relatively complex building that was designed by FEMIX. In the right part, we see the problem type with the components for defining the input data, part of the input data, and we see in the left the vertical displacement field for one of the combinations adopted in the analysis, in the design of this building. Well, this slide, we see the first floor where it was designed using a material nonlinear model. Since we intended to reduce the conventional reinforcement by steel fibers to minimize the distance between the bars of the conventional reinforcement for assuring good or proper casting conditions for the concretes. So we see the crack pattern, which was obtained by performing material nonlinear analysis with one of the cracking models available in FEMIX, and we use global resistance methods for this purpose. In the following slides, we will present two case studies or two structures that were designed with FEMIX, and in both we perform material nonlinear analysis because in fact again we used fiber-reinforced concrete, and since fibers are only activated after crack initiation, so it is fundamental to use a cracking model to simulate the benefits of fiber reinforcement. So we see here the cross-section of this long foundation. In the core part of the cross-section, we adopted insulation material to minimize the content of the concrete and also to minimize the peak temperature in this structure, and consequently to minimize the cracking risk. So we see here that in fact we only adopted one mesh of prefabricated steel bars. So it's a prefabricated grid mesh, so very easily to be installed, and then everything is made by concrete reinforced with polypropylene fibers. So to calibrate or to assess the predictive performance of the thermal model existing in FEMIX, the CV test and the laboratory of CV test install thermocouples in the critical regions of the structure, and then it was monitorized the variation of the temperature during the maturation or the curing of the fiber reinforced concrete. So this information was adopted, or this experimental records was used to compare with the model in FEMIX. So we simulated only half of the structure. We see here the core material, so the insulation material. The gray color is the concrete foundation, and then the surrounding in soil. So we also use interface between the concrete and surrounding soil. And here in the bottom part, we see the temperature field at the temperature of 25 degrees. And in right part, we see that in fact the model has a good agreement with the experimental records. So in this slide, we see a video of using GiD for the temperature field during the maturation of the concretes. From the experimental test carried out in laboratory of CV test, in terms of characterizing the post-cracking behavior of fiber reinforced concrete, and using a computational tool based on the inverse analysis, we were able to obtain the tensile stress as crack width that was used to simulate the fracture mode 1 propagation in the nonlinear material model that we use to simulate the behavior of this structure. So, well, considering the evolution of the mechanical properties of the concrete, considering the concrete maturity model coupled with the concept of equivalent age, and also considering the creep and the autogeneous and range leakage, we evaluate the cracking risk of this structure since early age. And we see in this graph the evolution of the temperature as well the evolution of the crack width, and consequently it was able to estimate the maximum crack width during the curing of the concrete. In this figure we see the crack pattern in one of the cross sections of the structure, and also the cracking pattern in plant view of the foundation at the temperature of 23 hours, so at critical moment where we have the highest or the larger crack width. So this is also a view of the crack pattern formed during the process of curing of the concrete, fiberglass concrete. Well, the second case is a huge pavement, industrial pavement made with a size of 135,000 square meters, of a thickness of 0.3 meters, and FEMIX was used to try to minimize the content of conventional reinforcement by its replacement by steel fiber reinforced concrete. So the conventional reinforcement was only disposed, because this pavement is supported on piles, so the conventional reinforcement was disposed along, is like a strip of conventional reinforcement disposed along the alignment of the piles in the bottom part of the slab, and then it was used fiber reinforced concrete. We designed the critical panel with a dimension of 32 by 38, and we adopted a steel fiber reinforced concrete of 5C toughness class according to the model code recommendations. So we used the ECOV global resistance methods to make the verification for service limit state and ultimate limit state conditions. So one critical moment is in fact the cracking risk during the early age of the fiber reinforced concrete. To make this analysis, it was necessary to simulate not only the surrounding pavement to the model that we analyzed, but also the surrounding soil to simulate the transference of temperature between the concrete and the surrounding soil. So we use, for this purpose, we adopted concrete maturation model, the concrete grip according to the Eurocode, and also the autogeneous shrinkage, everything according to the recommendations of Eurocode that is implemented in FEMIX. The verifications for service limit state was made in terms of crack width and deflection. So in this case, we see the crack pattern for one of the load combinations. So these load combinations introduce the maximum crack width in the bottom region of the pavement in the panels close to the crack control joint. In this case is another load combinations introducing the larger crack width in the intermediate panels. And in this case is a load combination that introduce the maximum crack width in the top part of the pavement over the piles, and in the right part we see finally another combination where these combinations introduce the maximum bending moments, positive bending moments in the intermediate panels, and we see clearly the formation of these cracks. Thank you very much.